in this example number 5, we are supposed to find the volume of the prism. So it's going to be about the volume of an object in three-dimensional space. And we also know about the base of this object too, right here. The base is going to be a triangle in the xy plane. So this is a second piece of the information that we learned from this problem about the base and its shape. And later on we get to know about the top of this object right here. The top surface of this object is going to lie in the plane z equal to this multivariable function f of x and y. Two variables, definitely a surface in 3D space. So we are talking about a volume, right, between base and top surface. Okay, combining all these elements, all these informations, we know right away we are working with a problem of double integral. So volume between base and top, this is definitely double integral. Okay, and not just that, we also know about the base of this object, which means that we know about the integration domain R of this double integral. And it turns out to have the shape of a triangle, which is non-rectangular, which means that we are looking at a general form of the integration domain. So here it's going to be general form of integration domain R. And that's going to be for the double integral in this example. And we are going to rely on the Fubini's theorem number 2 that we learned in the last lecture. And as you can recall, when it comes to general domain R, we need to pick the order of the integration wisely. We can't just pick any of them. We need to determine whether it's going to be dy dx or dx dy. That's going to make the calculation easier. So we need to pick the better one, the more suitable one. Either dy dx or dx dy. Which one is the better one? To answer this, we need to know the type of the integration domain R. Okay, so the first thing that we are supposed to do in this example is to determine the type. Once we know the type, we know the order of the integration. So the first thing, determine type again. Determine type of the integration domain R based on its shape. Based on shape of R. Since we need to see the shape of R, we need to plot it in the graph. So let's take a look at the integration domain, the information that they gave to us from the problem. So we are talking about the triangular integration domain R right here. So let me write it right here. Triangle R. So let's take a look at all the lines, all the curves that they give to us. So first curve, first line is going to be x-axis. So let's bring it here. Number 1 is going to be x-axis. But if you leave it like this, it's kind of hard to use x-axis. Sometimes we need to express it in terms of a function, and you can't just put it as x-axis. So let's change it to y equal to 0. It's the same thing. Horizontal axis happens when y equal to 0. Okay, so that is the first line. Now the next line is going to be y equal to x. Next line, y equal to x. Okay, and last one is going to be x equal to 1. X equal to 1. Now let's draw all these lines, all these curves into the graph down here. I know that all the lines are already available in the graph, but let's take a look at them and let's highlight them the way that we have information from the problem. So let's take a look at the graph on the left hand side. I'm going to start with the first one, x-axis or y equal to 0. It's going to be this one. Let me highlight this one. X-axis, of course this one is easy. First line. Next line is the y equal to x right here. Okay, so it's going to be a straight line with a slope of 1 and crosses the origin, and it's going to be this line right here. Okay, and the last one is going to be x equal to 1. So let's draw it right here, x equal to a constant value of 1, and it's going to be this solid line right here. Okay, let me fix this one. Okay, this looks a little bit better. Now, when you have all these three lines, you start to see the region trapped between them, right? And it's going to be this region between them. Okay, and it's going to be the integration domain R for this problem, the triangular R. Okay, now that we have the plot of this region, the next thing we are supposed to do is to determine the type of this region, whether it's type 1 or type 2. In order to determine, you need to ask yourself, when you look at this region, do you see two curves between upper and lower boundaries, or two curves between left and the right boundaries? Okay, so I look at this region, and at first glance, I see two curves between lower and the upper boundaries, like this. I see one at the lower boundary of this region, like at the base of this triangle, and another one at the upper boundary of this region. And it's going to be this one. Okay, so red at the base and blue at the top, definitely lower and the upper. That's how I see it at first glance. Since I see it this way, lower and upper, this is definitely type 1. Right? This is based on the Fubini's theorem number 2, so you can look that up if you forgot about that. This is definitely type 1, which means that the order of the integration has to be dy and dx. Okay, once you see the shape of the R in the space, you can determine the type. Once you know the type, you know the order of the integration. Okay, so now that I know about the two boundaries, lower and the upper, let me assign functions to them. Lower one is going to be g1 of x according to the formula of the theorem, and the upper one is going to be g2 of x. So these are the lower and the upper boundaries. What about the left and the right? Left and the right have to be constant. So left is going to be this right here, constant of A, and right is going to be constant right here, constant of B. So there you go, we have all these boundaries. Upper, lower, left, and the right. Now we can complete the double integrals down here. So let's work on this double integrals. Okay, of this function that we have, the top surface, it's going to be this multivariable function of 3 minus x minus y. So let's put that right here in the double integral. It's going to be 3 minus x minus y, and right now we know, at this point we know the order of the integration. It's going to be dy and then dx. So let's put that right here. Going to be dy and dx right here, which means that we are supposed to integrate with respect to y first. Okay? Alright, let me remind you about the rule that we have in the beginning. We always have to integrate between two curves first, right? So we are going to integrate between lower curve and the upper curve. So here I am going to integrate with respect to y. So integration sign, the inner one is going to be y, is going to be about y value, okay? And y value has to be equal to the lower curve, since we have to integrate between the curves first. So start with the lower curve, and I integrate until I reach the upper curve. Y equal to g2 of x for the upper curve. When I perform this integration, I create this sweeping pattern, starting from the lower curve and sweep up and ends at the upper curve. So we have this arrow right here, just one. Okay, now that I am done with the y variable, I can start to integrate this with respect to x. And for x, I need to integrate over its range, starting from x equal to a and ends at x equal to b. Okay, and when I do this, I am going to, during the time that I integrate with respect to x, I am going to create this arrow over and over again, the same pattern. Okay, when x variable increases, this is going to get copied again and again from the lower curve to the upper curve, and until you reach the upper limit of the x value, which is equal to b. And as you can see here, we have covered the whole region of this integration domain by using this sweeping pattern. Okay. All right, now let's take a look at the details of this boundaries that we have in terms of AB and G1x and G2x. Okay, start with G2x or G1x, lower curve. Okay, G1x right here. This is the lower curve, and as you can see here, it's supposed to be expressed as a function of x. So let's take a look at this lower curve. This is a line right here, x-axis. So it's going to be about this line. Okay, x-axis. So which means that this is y equal to 0. So G1x right here is going to be equal to 0 in terms of x, function of x right here. Okay, and in the end, this is going to get assigned to this y variable, just like right here. Okay, so we have this function defined as equal to 0, G1x equal to 0. Now G2x right here, G2x, we need to express this line as a function of x, and let's take a look at this line. The upper curve, G2 of x, it's going to be this straight line, and it corresponds to this line right here, y equal to x. So looking at this, I want to express this in terms of x or constant. Of course, it has to be x. G1x equal to x, and later on this gets assigned to this y variable. Okay, so let's put a box around this. Okay, function of x can have x in there or has a constant like this 0. Okay, that's why we have 0 right here as a function of x and x right here as a function of x. Alright, that is G1x and G2x. What about a and b? So let's take a look here. A is going to be definitely 0, right? And b right here is going to be equal to 1. Okay, so let me put it right here. A is going to be equal to x equal to 0, right? And b, constant, going to be equal to x equal to 1. So we have this for a and b. So there you go. Once you have all these four values, G1x, G2x, a and b, you can put them into the double integrals and you can start solving them. Okay? So that is the, as you can see here, for this triangle R, we can see type 1 on the first glance. But on the second glance, you may see something different. Or you may have seen this from the beginning. When I say that I see two curves between lower and upper, you might disagree with me. You might say, no, I don't see that. Instead of lower and upper, I see left and right, using the same region. Okay, so let's take a look at the one on the right hand side. Instead of lower and upper, you say that, hey, I see something like this. One on the left hand side, okay, the left hand of this triangle, and another one at the right hand side of this triangle. Okay, well, it sort of makes sense. Red can be interpreted as the left hand boundary of this region, right? It's on the left hand of this region, and blue on the right hand. It's not wrong, which means that, hey, you can use type 2 for this integration domain too. Type 2 is going to work here as well. Type 2 means that you can choose the integration order as dx dy. Okay. Okay, on the second glance, this seems to be type 2 as well. So let's take a look whether it's going to cover the whole region like we did with type 1. So let's try that out. Okay, so let's assume that the left one is a function and it's going to be a function of y, h1 of y, and the right boundary is going to be h2 of y, like how we defined it in the theorem for type 2. Okay, all right, now that h1y and h2y is the boundaries for the x variable. Now for the y variable, you can see that y can start from the range for y starts from c and ends at d. Okay, now let's try to work this out just like we did before. Double integral, okay, of this same multivariable function 3 minus x minus y, and this time around it's going to be with respect to x first and then y later. So we have this dx dy. Okay, now let's put everything in. Once again, we are going to integrate between two curves first, this rule of thumb. So it's going to be with respect to x first, which means that x is going to start at the left hand curve, which is going to be this red one, h1 of y. And we are going to integrate to the right hand curve, which is x equal to h2 of y. Alright, and when you do this, you are going to sweep starting at, well, y equal to c, the lower limit of y, sweep from the left curve to the right curve. So you create this sweeping pattern. Okay? Alright, now once you are done with the x variable, you can proceed to integrate with respect to y, and y is going to start at y equal to c and then keeps increasing until y gets to d. So during this process, this arrow is going to get replicated or copied like this. As y value increases, this is going to repeat itself again and again until y reaches d value right here. And as you can see, we covered the whole region of this integration domain just like we did with type 1, which means that for this particular problem, example number 5, you can choose either type to work on this double integral. So you can make a note right here that, well, both type work for this problem. Okay, so you can pick either one and they should come out to be the same, come out to be equal. All right, now let's take a look at the details of this h1y, h2y, c, and d. So let's take a look at this one first. h1y. Okay, h1y has to be a function of y. Now let's take a look at the line that represent the left hand boundaries. So it's going to be this straight line, right? So it's going to be this, y equal to x. We need to express this in terms of y. Of course, it has to be equal to y. In terms of y, so this has to be equal to y, which later on gets assigned to this x variable. Okay, now, next one. We have this h2 of y. We need to express this line as a function of y or constant. So here we have this right here in terms of y, and the right boundary is this one, and it's going to be this, x equal to 1. We need to express this in terms of y or a constant, definitely constant of 1. So this h2y equal to 1, and once we are done with this, this is going to get assigned to x value during the integration. Okay, now for C and D, not so bad, right? Quite easy. C right here is going to be 0, and D right here is going to be equal to 1. So you can right here, C equal to 0 and D equal to 1. Okay, so for this example, you can work with either types, either ways. Since both ways are supposed to work, why don't we try both of them? So let's do it quickly here. Example number 5 again, and this time I am going to work with type 1. First case, let's assume that we have this lower boundary right here and the upper one right here. Okay, so this is what we are going to do on this slide using type 1 to solve this example. Okay, so it's going to be type 1, and type 1 is dy dx, and let's bring the double integrals that we have before. Double integrals. Okay, and we have this function 3 minus x minus y, alright, with respect to y first and then x later. Now we have defined the all this g1x. Okay, by the way, let me put it again. g1 of x right here, and let me put g2 of x right here. g1 of x, we have defined it to be equal to 0, and g2 of x to be equal to x. Okay, as a function of x, which means that we can complete it right here. This is going to be equal to x equal to 0, g1x. Okay, and up here is going to be g2 of x, and that's x equal to, I am sorry, this is supposed to be y. we are integrating with respect to y, so here is supposed to be y. Sorry about that. Supposed to be y, right? And then y right here equal to the upper curve, that's g2x, and that's equal to x right here. So y equal to x right here. For x, we integrate from the x equal to 0. C right here equal to 0, and a right here equal to 0, and b right here equal to 1. So this is going to be, let me use black, x equal to a, which is 0, and x equal to b, which is 1. So there you go. Okay, so I'm sorry about this. This is supposed to be y because we are working with y first. Okay, at this point, everything should be easy to work on. Now we are going to integrate this with respect to y first. Okay, once again, integrate with respect to y first, which means that we are supposed to treat x as constant. Okay, let's work on this. Let's integrate this with respect to y. So of course I am going to get this. Okay, equal to, go to right here, integrate 3 with respect to y, I get 3y. Okay, what about I can save some space since we have plenty of space right here. Let me work right here, equal to, integrate 3 with respect to y, I get 3y. Integrate x with respect to y, I get minus xy. Okay, minus xy. Integrate this y with respect to y, I get minus y squared over 2. Minus y squared over 2. And I am supposed to evaluate this at two values of y. Y equal to 0 and y equal to x. And don't forget the other integration sign right here with respect to x. And this is supposed to go from x equal to 0 and ends at x equal to 1. Alright, now y equal to x goes in here. So I am going to get 3x Okay, and y equal to x goes in here. I am supposed to get minus x squared. Minus x squared. And y equal to x goes in here. I get minus x squared over 2. Minus x squared over 2. Okay, and I am supposed to subtract the other term. This y equal to 0 goes in here. It's going to go to 0, right? Y equal to 0, same thing, 0. Right here, same thing. So in the end, this is going to be equal to 0. I can ignore this term. Alright, and what about I combine these two? It's going to be equal to minus 3x squared over 2. And I still have this integration. X equal to 0, x equal to 1, and dx. Okay, so let's clean this up. It's going to be equal to, okay, integration of x equal to 0 to x equal to 1, just the same. We have this 3x minus 3x squared over 2. And we are supposed to integrate this with respect to x. And this with respect to x, I get 3x squared over 2. 3x squared over 2. This with respect to x, I get x cubed over 3, and 3 cancel with one another, so I get x cubed over 2. And I need to evaluate this at two values of x equal to 0 and x equal to 1. 1 goes in, I get 3 over 2. 1 goes in, I get 1 over 2. Right, the other term, 0 goes in, it's going to go to 0. 0 goes in, going to go to 0. So just like before, I get 0 as the second term. Okay, nothing is going to happen here. So 3 over 2 minus 1 over 2. In the end, I get this 1 as the answer for this example 5, and that's going to be the volume of the prism between this base of triangle and this multivariable function of 3 minus x minus y. So this, you can make a note that this is going to be cubic unit, or you can say unit cube right here. Unit cube volume of prism. And we just worked on type 1. Alright, now why don't we try type 2 really quickly. So type 2, just like we have pointed out, is going to be two curves between left and right. So one curved over here, alright, and another curve right here, two boundaries, left and right. So we have this h1 of y on the left and h2 of y on the right. And let me put all the information that we have before. h1 of y is going to be equal to y. And h2 of y right here is going to be equal to 1, a constant. Okay, now for c and d, c is going to be equal to 0, and d right here is going to be equal to 1. And this time it's going to be viewed as type 2. Let's find out if we look at it differently, and can it give us the same answer. So sweeping from left to right again and again until we cover the whole region. Okay, so let me check the pattern right here. Okay, so type 2, it's going to be this order, dx, dy. Now, what about the double integrals? Let's put everything into this double integral right here. 3 minus x minus y. This time it's going to be dx and dy. Okay, now first we integrate with respect to x first. So this is going to be x value, right? No same mistake again. Okay, x lower one is going to be equal to the left hand boundaries, and it's going to be this h1 of y. So this is equal to y, so I can just put y right here. X equal to y. and I integrate from left to right. 2h2 of y, and this one is equal to 1, so I can just put 1 right here because it's equal to 1 right here, and the previous one is equal to y, and it corresponds to the values in the integral. Alright, now we are done with the x variable. Now for the y variable, easy, from 0 to 1. Okay, y starts from 0 and ends at 1. There you go, we have the complete double integrals for this type 2. Now let's try it out. First, we are supposed to integrate the inside integration integral. This one with respect to x first. Let me check something. Okay. Integrate with respect to, this time, x first, which means that treat y as constant. Okay, let's work on that. I'm going to work right here. So let's integrate this with respect to x. I get 3x. This with respect to x, I get minus x squared over 2. Minus x squared over 2, and this with respect to x, I get yx. Minus yx, because y is a constant to x right here. So y stays the same. Alright, and then I am supposed to evaluate this at two values of x equal to y, and x equal to 1 right here. And the other integration with respect to y, starting from y equals 0 and ends at y equal to 1. Okay, now what we need to do right here is to put x equal to 1 in here and also here. So I'm going to get 3 minus 1 over 2 minus y for the first value of x, right? Minus, now I work on this y right here. Goes in here, x equal to y, x equal to y, and x equal to y. So first one, it's going to be 3y, x equal to y, so this becomes 3y. Next one I have minus x squared over 2, but x equal to y now, so it's going to be minus y squared over 2. And x goes in here, right here as y, which means that in the end I have this minus y squared. Minus y squared. Notice that right now everything is in terms of y. X is gone. So if you work on the first integral and it turns out that you still have x left, then something is wrong. Okay? At this point, all y. Okay, so we are supposed to integrate this. Okay? With respect to y. Okay, let me work this out. So this 3 and minus 1 over 2, it's going to be 5 over 2 minus y minus 3y, that's minus 4y, and we have this, okay, plus 3y squared over 2. Okay, so let's work on that over here. So here we are going to have this equal to 5 over 2 minus 4y and plus 3y squared over 2, and integrate this with respect to y from y equal to 0 and ends at y equal to 1. So here I have 5 over 2y minus 2y squared. Okay, integrate 3y squared over 2, I get y cubed over 3, so in the end I have this y cubed over 2, and I am supposed to evaluate this at two values of y equal to 0 and y equal to 1. So 1 goes in here all the way through. I am going to get 5 over 2 minus 2 plus 1 over 2. So the other term, 0 goes in, goes to 0, goes to 0, and same thing. So next term is going to be 0. I don't need to worry about that. So here 5 over 2 plus 1 over 2, I get 3, minus 2, I get 1. Same answer as what we got previously using type 1 to calculate. Here we use type 2 and we got this 1 cubic unit cube for the volume of the prism. And we are talking about the same object, same prism, right? They must have the same volume. So let's make a note right here that this once again is the volume of prism, except that this time we apply the type 2 approach to perform the calculation. And since the result for type 1 and type 2 is the same, let's make a note down here that the result we got in this slide is the same as type 1. But this statement, same as type 1, is only true for this example. For this example only. They might not be the same for other examples or other problems, and the reason for that is because of the shape of the integration domain. In this example, we are working with a triangle that applies to both types. The triangle that we have here can be considered to have two curves between lower and upper, or between left and right, and that's why the results for both types come out to be the same. Okay, so let's move to example number 6 right here. In this example, we are supposed to evaluate this double integral, so let's make a box around that. What is convenient about this problem is that we don't need to decide the order of the integration because it's given to us. They already told us that the order has to be this: integrate with respect to x first and then y later. So they already told us that this is type 2 without having to decide or to figure out anything. It's already type 2. And then we are supposed to draw the integration domain, alright? So we are supposed to draw this r in the graph and then evaluate this double integral. So let's get started. Okay, type 2. This means that we have functions for left and right. We are talking about h1 of y and h2 of y. And this came from the formula in the theorem. So let's take a look at this h1y and h2y first. So h1y is going to be the left curve, right? So you can make a note right here. This one is supposed to be the left curve and this one is supposed to be the right curve. And as you know, we have this one rule. We are supposed to integrate between these two curves first. So this 0 right here is the left curve. And this ln y right here is the right curve. Left curve and right curve, which means that h1 of y is going to be equal to 0. Okay? And this h2 of y is going to be equal to ln of y. Alright? As a function of y, and we have y right here. So, no problem. And then what do we know next? The range for the y variable. So y right here is going to be related to this one right here. So this one is going to be c equal to 1 and ends at d equal to ln 8. Okay? So we know that c is going to be equal to 1 and d equal to ln 8. And we are going to use this information to draw the graph. So let's draw some axes right here. So let's assume we have this y-axis and maybe x-axis like this. So let's take a look at this one first. This is supposed to be x value, so this is x equal to 0. X equal to 0 is going to be y-axis. So you can translate this x equal to 0 to y-axis. So we are going to start with this y-axis right here, the first boundary. Okay, and it's supposed to be on the left side, right? So this one is on the left and this one is on the right. Okay, now let's take a look at this. We have this h2y, and once again this is going to get assigned to x, which means that we have this x equal to ln y curve. So we are supposed to plot this curve on the graph, but I like to look at this equation this way, as a function of y. So it's going to be equivalent to y equal to e to the power of x. I just move things around to make y alone on one side. So I have this, and I am going to plot this on the graph as the second curve. So y equal to e to the power of x, it's going to be something like this. Okay, exponential. Alright. Okay, so it's going to cross the y-axis at y equal to 1, right here. Okay, let me fix that. This is supposed to be equal to 1. Okay, this is y-axis and x-axis. Now the range for y goes from 1 to ln 8. So it's going to start right here. 1 to maybe ln 8 around here. Okay, this is just an estimation. So this is about ln 8, which is for d value, and 1 right here for c value. So we are talking about left boundary as this red line, right boundary as this blue line. Okay, and we have this upper boundary as a constant ln 8, and lower boundary as a constant 1. So we are talking about this integration domain R that looks like this, between y-axis and the curve of the exponential of x. Okay, so that is the domain region in the graph. Now we are supposed to evaluate this double integral. So let's work on that. Okay, so we are going to start with this double integral. Once again, let's start with this one. Okay. Let me save some space. I am not sure how much space I need. Okay, so it's going to be double integral of e to the power of x plus y. Alright, and we are going to integrate with respect to x first, and then with respect to y later. And then this is supposed to be integration with x, right? With respect to x, right? So this first integration sign is going to be x value. Is going to be equal to, according to this right here, equal to 0. And x value right here, same thing, equal to ln y. Okay, and next one is going to be this c equal to 1. So that's going to be y equal to 1 and ends at y equal to ln 8. And just like we did before, we are supposed to start with the inner integral, which is this one, inside one, and we are supposed to integrate this with respect to x. Integrate with respect to x first, and just like last time, it's going to be, we are going to treat y as a constant during the process. Y as constant. Okay, so let's do that. We are going to integrate this e to the power of x plus y with respect to x. We integrate exponential, we get the same thing, right? Okay, so I'm going to work right here. Equal to, I get the same thing, e to the power of x plus y, and that is it. And I need to evaluate this at two value of x equal to 0 and x equal to ln y. And I need to integrate this again with respect to y from 1 to y equal to ln 8. Now, the values of x has to go in. X equal to ln y has to go in here. So I am going to get this e to the power of ln y plus y. That's the first term. Minus the second term, 0 goes in here. So it's going to be e to the power of 0 plus y. Okay? 0 plus y, and this integration, y equal to 1 and y equal to ln 8. And this integration with respect to y. So let me work on this before I write the whole term. So this is going to be equal to e to the power of ln y times e to the power of y minus e to the power of y. E to the power of ln y is going to be equal to y. Alright? Times e to the power of y minus e to the power of y. So I take the common term and I get this e to the power of y with the y minus 1 inside the parenthesis. Okay? Once again, you see this, e to the power of ln y, the result has to be, well, they are inverse functions, right? Exponential and logarithm, so they cancel and you get y out of that. So you are supposed to integrate this remaining term with respect to y, starting from y equal to 1 and then stop at y equal to ln 8. Now, let's take a look here. We are looking at two locations of y inside this term. Y is right here and also y right here. So we are looking at a product of two sub-functions of y. And it seems like I can't integrate this directly. Okay? So let's take a look at this. It doesn't seem like we can integrate this directly because we are looking at this as function, first function of y, f of y, and this times with another sub-function of y, g of x. G of y, I'm sorry. Does this remind you of anything? When you run into a situation like this, you can't perform the integration right away and you notice this pattern, a product of two sub-functions, then there is a chance that you might need to apply the by parts, integration by parts. So, make a note right here. You see a product of two sub-functions of y. Alright, so we are talking about this f of y times another g of y, and you can't seem to integrate this directly. So let's apply integration by parts. Integration by parts. And can you remember the formula for that? And well, it's going to be this: integrate u dv equal to u times v minus integrate v du. Okay, so we need to pick which term is going to be u and which term is going to be dv. Okay, so we need to make a decision here. Which one is going to be u and which one is going to be dv. And now let's take a look at the formula that we have here. So we have u in this formula right here, and in the end we are supposed to find this du, which means that we are supposed to be able to diff u without any problem. Okay, we are supposed to be able to diff this u. Okay, now for this dv in this formula, dv, and we have v right here, it means that we are supposed to be able to integrate dv so that we can have this v to fill in the formula. So dv has to be able to integrate. So I need to pick whether I'm going to choose this as u or this as u. So I ask myself, can I diff e to the power of y? Yes, I can. Can I diff this y minus 1? Yes, I can. So either one is good for u. What about dv? Can I integrate? can I integrate e to the power of y? Yes, I can. And can I integrate y minus 1? Well, yes, I can. And it turns out that both of them are fine with dv. But which one is better? Now, here's the important thing. When you diff something or integrate some terms right here, you expect it to be more simple. Alright? So let's ask ourselves again. If you diff e to the power of y, do you get a simpler term? When you diff this, do you get a simpler term? The answer is no, because you get the same e to the power of y, right? Now the question is, if you diff this, do you get a simpler term? Well, yes, if you diff this y minus 1, you get 1. So this is the better one for the u. And that's why I choose u to be equal to y minus 1, because I know if I diff this, y minus 1 would become 1, and it's simpler than the y minus 1. Now for dv, let's ask ourselves, do I get anything simpler by integrating this e to the power of y? Well, it's the same, right? So nothing changes. What about if I integrate this? Do I get anything simpler? But it turns out that if I integrate y minus 1, I get y squared over 2 minus y. It gets more complex. So I wouldn't assign dv to y minus 1 because it's going to get worse than before. So for dv, e to the power of y is more suitable. And that's how I chose these two terms, based on the ability to diff, ability to integrate, and whether the result is more simple or more complex. Okay? Now let's work on these two terms. du by dy is going to be equal to 1. Okay? And I am going to integrate dv both sides, and in the end I have this v equal to e to the power of y. So there you go. So I have this du and dv ready to fill in the biparts formula. So here I have this integrate. So let me write this again. Integrate e to the power of y. Okay, and oh, by the way, let me do this. I'm going to put u in front to make it more clear. So u is going to be y minus 1. Y minus 1, that is u, times dv, which is e to the power of y dy. So let's write it down right here, that this one is u and this one is dv. Okay, and this is from y equal to 1 to y equal to ln 8. Now we follow the formula. We have this equal to u times v. So let's take a look here. This is u. We have it right here. So u equal to y minus 1 times v right here. V is right here, equal to e to the power of y. E to the power of y. Okay. And we are supposed to evaluate this at 1 and ln 8. So you can make a note right here that what you see right here is u times v. Okay? Now minus, integrate, same thing, 1 to ln 8. V, do we have that? We have it right here. V equal to e to the power of y. What about du? We need du right here. And du is going to be equal to dy based on this equation. Du equal to dy. Okay, so you can make a note that this term right here is v and this one right here is du. Okay, now all we need to do is to work out the right side of this equation. Okay, so this is going to be equal to ln 8 goes in, it becomes, right, ln 8 goes in here as y and goes in here as y. So this is going to be ln 8 minus 1 e to the power of ln 8. Okay, that's the first term. Minus 1 goes in as y, right here. So you are going to get 1 minus 1. So it's going to be 0 for the second term. Okay. So that is it for the first, the front term. So we have this parenthesis over them. Minus integration of this e to the power of y. You integrate e to the power of y with respect to y, you get same term, e to the power of y. And you are supposed to evaluate this at two value of y equal to 1 and y equal to ln 8. So in the end, I have this. Oh, by the way, you see this e to the power of ln 8? This is equal to 8. Okay, exponential meets with natural log. You cancel each other, so you get 8 out of that. So in the end, this is supposed to be 8 ln 8 minus 8. Okay, minus this term, ln 8 goes in. It's going to be e to the power of ln 8. Okay, and 1 goes in. It's going to be e. Okay, minus e. So in the end, you have this equal to. Alright, so let me check. It's going to be, by the way, this is going to be 8 again. And in the end, you have this 8 ln 8 plus e minus 16 as the final answer for this example. Okay, so what makes this example a little bit more difficult is the application of biparts. So if you forgot about that, you might need to look at that stuff again. Okay, so now that we are done with example 6, we can move to example 7 right here. So I'm going to skip this one. Okay, same as example 6. So let's move to example 7 right here. Okay, in this example, we need to calculate this double integral of some multivariable function, this one, 16 minus x squared minus y squared. So this one is going to be function of x and y, and it's supposed to be a surface in the three-dimensional space. And we are supposed to find the double integrals of this surface with respect to differential area. When you see dA like this, it means that we don't know the order of the integration, whether it's dx dy or dy dx. Okay, let's make a note right here. Dx dy or dy dx, we don't know, and we need to determine that, right? We need to find a way, and we are supposed to perform the integration over this integration domain R. And let's take a look at the information that we have for this R. It's going to be enclosed by 3 curves. So the first curve is going to be y equal to 2 square root of x. That's the first one. Second one is y equal to 4x minus 2. And last one is x-axis. And by now we know that x-axis is the same as y equal to 0. Okay, 3 lines. Definitely general form. Okay, general R. And we need to determine the type in order to pick whether we should go with dx dy or dy dx. So the first goal, once again, is going to be about determining the type of this integration domain R. Determine type based on shape of R. So we need to do some plotting. Okay, so let's do it right here on the left hand side. Let's assume that we have this y-axis right here. Okay, and x-axis something like this. Okay, now let me extend this to be a little bit longer. Okay, should be better. So this is y-axis and this is x. So let's start with this first curve, y equal to 2 square root of x. It's going to be something like this, square root of x and 2 times that. Okay, keeps going up. Okay, so let's make a note here that this is supposed to be y equal to 2 square root of x. Now, last one is easier. Let's take a look at this x-axis. It's going to be this one. Alright, x-axis, easy. Now, let's take a look at this. Y equal to 4x minus 2. So, let's take a look at what happens when y equal to 0 with this. So if y equal to 0, 0 equal to 4x minus 2, and we get, oh, this is supposed to be minus, okay, minus 2, and this we get x equal to 0.5, which means that when y equal to 0, x-axis, x is going to be equal to 0.5, so we have a small scale right here, 0.25 around here, 0.5, 0.5, and let me make this 0.75, and some around here, 1. So it's going to be a straight line with a slope of 4 and crosses x-axis at x equal to 0.5. So maybe something like this. I'm going to guess something like that. Straight line. Okay? Should be close enough. So there you go. We have 3 lines and you see the region trapped between them, right? So first line is the square root of x times 2. Straight line with a slope of 4 and x-axis. So we have this region trapped between them. So this is the integration domain for this double integral. Okay, first of all, let's find this intersection. I need to know where that is. And it's going to be the intersection between this curve 2 square root of x equal to the other one 4x minus 2. Okay. Okay, let's square both sides. So this is going to be 4x. This is going to be 16x squared minus 16. Okay, minus 16x and plus 4. Okay, so let's divide 4 on both sides of this equation. You are going to get this x. Okay, I'm sorry. This is supposed to be x equal to, divide by 4, you get 4x squared minus 4x and plus 1. So I'm going to move things around and I get this 0 equal to 4x squared minus 5x plus 1. And I do some factorization. I get this 4x minus 1 and x minus 1 and 0. So I can see that this is going to have intersection at x equal to 1 over 4 and 1. And since this point is further away than this 0.5, right? So this point has to be greater than 0.5. So it's going to be this point, right? Because it has to be greater than 0.5, which means that this point is going to happen at exactly x equal to 1 right here. So you can put a coordinate right here. So this is going to be a point at x equal to 1, and when you put 1 to this equation, you get y equal to 2. So you get this point. So there you go. Okay, all the intersection and all the boundaries. Now the next thing we are supposed to do is to determine the type of this region, whether it's going to be type 1 with the curves between upper and lower, or the type 2 with the curves between left and right. So let's start with the first one. What if I see the curves between upper and lower? What if I see this as the upper curve? Let's assume that. If I see this, then I need to find the lower curve. But it turns out that the lower curve would have two sections. One right here and another one right here. That is not going to be easy because we are looking at two different equations and two different functions for the lower bounds. So what about I try something else? What about I try to look at this as lower left curve and the right curve, whether it's going to work out, because upper and lower is going to be a little bit complicated. What about I assign this to be the left curve? This looks good. Okay, of the region. And when I see this as the left curve of the region, I suddenly see this line as the right curve, the right border or boundary of this region, right? Okay, so with this, I can assign this to be function h1 of y, and this to be function of h2 of y. And at this point, I know it's going to be type 2. Okay, type 2. And type 2 is going to be dx dy, which means that you are going to integrate with respect to x first. So you are going to sweep it like this, horizontally, from the left curve to the right curve. And once you integrate with y, you are going to copy this arrow again and again until you cover the whole region. So this looks good. So let's try that. So we are supposed to find this double integral. I am going to start working right here. Double integral. Okay. Okay, what about here? This is better. Let's start with this double integral. And it's going to be over this multi-variable function 16 minus x squared minus y squared. So it's going to be this 16 minus x squared minus y squared. And since I know this is type 2, it's going to be an integration with respect to x first and then y later. Okay? So I need to, first of all, let me put this. This is supposed to be x value equal to h1 of y, according to the formula for the Fubini's theorem number 2, and this x equal to h2 of y. Between two curves, this one is left curve and this one is right curve. And for the y value, for the range of y, so we need to look at this. Y is going to start at this point c equal to 0 and ends right here at the top of this region at the intersection, and it's going to be equal to 2. D equal to 2. So here we have this c, y equal to c, which is 0, and y equal to d, which is 2. Now we need to find out about this h1 of y and h2 of y. We need to find the expression for those two. So let's take a look here. I am going to work on this side. First of all, I'm going to start with this h1 of y. Okay? h1 of y is going to be this curve. Supposed to be this 2 square root of x. So I take a look at this. I take a look at this equation. But when I see this equation, this is expressed as a function of x. As you can see here, y as a function of x. So I cannot just put this right here. Equal to 2 square root of x is not going to make any sense. Because we are looking at a function of y, you can't put x in here. So we have to move things around to make this y equal to 2 square root of x to be expressed in terms of y. So I am going to erase this. So let me start with this equation right here. We have this equation, but it's not ready to be used right away. So I am going to move things around so that I have x on one side like this, and this becomes y squared over 4. So there you go. We have this x as a function of y, which means that I can assign this h h1 of y to be equal to this term, equal to y squared over 4. So there you go. h1y equal to y squared over 4 as a function of y. Okay? Now, I need this h2 of y, and it has to be expressed in terms of y. But let's take a look here. h2 of y is the right curve, and it's going to be this line right here, the straight line. And the equation for that line is this one. But once again, this equation is expressed as a function of x. I cannot just put 4x minus 2 right here. I can't, because this is supposed to be function of y, so this is wrong. So I'm going to start with this equation that they give to us, y equal to 4x minus 2. And I'm going to move things around so that x is alone on one side, x equal to y plus 2 over 4. So there you go, I have x as a function of y, just like I did up here. So I can use this, x as a function of y, right here on this function h2y, y plus 2 over 4. So there you go. Alright, so that is h2y, and in the end this is going to get assigned to x value in the integral. Same thing here, get assigned to x value. Alright, now back to the double integral. Now that we know about c, d, h1y and h2y, let's put everything into this integration sign. So it's going to be double integral. Same function, 16 minus x squared minus y squared dx dy. Now we know that h1y is going to be equal to y squared over 4. So this x starts at the left curve, and that is x equal to y squared over 4, and ends at the right curve, x equal to y plus 2 divided by 4. Okay, now c and d, y is going to start at 0 and ends at y equal to 2. Alright, so with this we can start with the inner integral with respect to x. Okay, integrate with respect to x first. Okay, so let's do it right here. So it's going to be equal to, I am going to integrate this with respect to x. This is going to be 16 of x, and minus, integrate this with respect to x. It's going to be x cubed over 3. X cubed over 3. Integrate this with respect to x. Y squared is going to get treated as a constant. So it's going to stay the same, y squared, and we have this extra x at the end. Alright, and once again, we are supposed to evaluate this at two values of x. X equal to y plus 2 over 4, and x equal to y squared over 4. Okay, now don't forget the other integration sign with respect to y in the end. Okay, and this is supposed to be integration from y equal to 0 and ends at y equal to 2. Okay, two values of x has to go in, and it's not going to be pretty because each one of them is sort of messy, right? So let's take a look here. X as y plus 2 over 4 has to go in here, has to go in here, and has to go in here. So let's take a look here. 16 stay the same. X as y plus 2 over 4 minus 1 over 3 stays the same. X cubed is going to be y plus 2 over 4 cube minus y squared stays the same, times x is going to be equal to y plus 2 over 4, and that is the first term. Okay, so this first term right here is supposed to minus the other term right here, another value of x has to go in here, here, and here. So second term, I'm going to draw it, I'm going to write it down here. 16 stays the same, y squared over 4 this time. Same constant, 1 over 3, y squared over 4. Cube, y squared stays the same. And this x equal to y squared over 4. Okay, and that is the second term. Okay, and we are supposed to close this, all these terms. We need to work it out. All this y cubed and y to the power of 4, and in the end we are supposed to integrate this whole term, all these terms with respect to y, starting from y equal to 0 and ends at y equal to 2. And after some painful calculation and hard work, you are going to get this number for the answer. I need to put this into a calculator and get this number out. I cannot work on this using hand. Well, I can, but it's going to take too much time. In the end, if you work this right, it's going to come out to be equal to 12.4. Okay? Alright. So you can make a note right here that after lots of work. Okay, so there you go. This is how you pick the boundaries so that in the end you can cover the whole region. But it turns out that in this example we can choose the boundaries and the type a little bit differently. So let's take a look at this other variation of this example number 7. So once again I am going to draw the integration domain in the space again. So we have this. I am going to repeat the figure. So it's going to be this y-axis and x-axis, and we have this first curve, y equal to 2 square root of x. So it's going to be something like this. Okay, and we have this scale 0.5 to 5, 0.5, okay, 0. Okay, let me work on that, I'm sorry. 0.5, and this one supposed to be 0.75, and last one 1. And we have this straight line with the slope of 1 and crosses right here at 0.5 and supposed to intersect with the previous curve at 1. I didn't do a very good job. So let me pick this one first. This might be easier. Okay, so there you go. So we have this same region, integration domain. Okay, this is supposed to be R right here. And before we have this left curve and the right curve, what about we want to use type 1? We insist on using type 1. What's gonna happen? I want to use this type 1, no other option. So I insist on this dy dx. So what's going to happen right here? First of all, we are supposed to have upper curve and the lower curve for type 1. So upper curve is quite obvious. It has to be this, right? Upper curve. Only one. And it's the upper border of this region. Okay, no problem with that. But the lower border or the boundaries of this region, it has two sections. One right here, which is x-axis, right? And another one right here, which is the straight line. Okay, so we can't use just one function for the lower boundary, but that doesn't mean that we cannot use type 1. We can if we split this region into two parts. We can do this by split this region into two sections. Okay, section 1 right here, section 2 right here. And as you can see, when you split it like this, section 1 is going to have this blue as the upper curve, upper boundary, and this red is going to be the lower boundary. And let's assign the lower boundary to be g1 of x and the upper boundary to be g2 of x. Okay, this one is supposed to be g2 of x. Now let's take a look at the section 2. Upper curve is still obvious. This is going to be the same, g2 of x. But here we have a different lower curve, lower boundary. It's going to be this straight line. So let's assign this to be g3 of x. Okay, so here we can start to perform the integration with this order of integration dy dx. Integrate with y first and then x later. Y first, we are going to sweep like this from lower curve to the upper curve. And once we integrate with x, we are going to replicate this. Okay, all the way. And we are going to stop right in the middle. So let's work on this portion first. So this portion is going to be this double integral. Okay, double integral of the same function 16 minus x squared minus y squared, and we insist on using this order dy dx, and this is going to be from the lower curve, and this is supposed to be y equal to lower curve is this g1 of x, g1 of x to upper curve g2 of x, and we integrate with respect to y first, right? So this is supposed to be y. Okay, so that is the first section of this region. Okay, now let's take a look at the second integration, the outside integration with respect to x. Now we need to know the range of this x right here. X start at a equal to 0 right here, 0. And for this portion, for this section, x is going to end at x equal to 0.5. Okay, so we have this. X start at 0 and ends at x equal to 0.5. Right here, we are looking at this first section of the integration domain. Okay? Now we are done with this first double integral, dy dx. But then we are supposed to work on another one, right? So I'm going to put it right here. Another one is going to be double integral again. All right, same function, 16 minus x squared minus y squared. We integrate with respect to y first and x later, just the same. But this time we are going to start with this second section. Sweep from the lower curve to the upper curve. Lower curve to the upper curve. And once x value increases, we are going to copy this arrow over and over until the end. We can cover the whole region, right? But we need to do this twice. So this time around, y starts at the it's going to be another lower curve, g3 of x. Starts from the lower curve, g3 of x, a different one. Okay, and ends at the upper curve, same thing, y equal to g2 of x. What about x value? X start at 0.5 and ends at 1. Okay, 1 right here. So this is the second section. X starts at 0.5 and ends at 1. So there you go. Now we need to find out about these g1x, g2x, and g3x. Why don't we start with this g1 of x? Okay. So g1 of x is x-axis. Okay, so it's going to be this x-axis, and we know this is y equal to 0. So g1 of x, let me write it right here, is supposed to be expressed as a function of x or a constant. So we are looking at this y equal to 0. So definitely this is going to be equal to 0. Okay? And what about g2 of x? g2 of x is going to correspond to this upper curve. This one should be easy. We just need to look at this y equal to 2 square root of x. So we need to express this equation as a function of x. So we already have that, 2 square root of x. 2 square root of x. What about g3 of x? g3 of x is going to be this line right here, straight line with this slope of 4. So it's going to be this equation, and we need to express this as a function of x, which is already good. 4x minus 2, this is already function of x. So we have this, we can use 4x minus 2 right away. Okay, so we know g1x, g2x, g3x, and everything, so we can complete the whole double integration. So we are supposed to find this double integral over this integration domain R, the whole thing, 16 minus x squared minus y squared dA. It's going to be equal to the sum of these two double integrals. So first, double integral is the first section, 16 minus, well, what about I write it right here? Okay, so we are supposed to find this double integral, 16 minus x squared minus y squared with respect to differential area. And we are supposed to work on this entire integration domain R. So make a note that R here is the entire domain. But we insist on using type 1, and that's why we are supposed to split the region into two parts. First part is going to be this. Same function, 16 minus x squared minus y squared, dy dx, and this is y equal to g1 of x, which is this, y equal to 0. Okay, and sweep to y equal to g2 of x, which is this, 2 square root of x. And for the range of x, x start at x equal to 0 and ends at x equal to 0.5, x equal to 0, and x equal to 0.5. So that is the first section of this region. Okay, now we need to add the other section into this double integral. So here comes the second one. Second double integral. 16 minus x squared minus y squared. Once again, this is type 1, dy dx. Integrate between lower curve, this one, y equal to, lower curve is the straight line with a slope of 4, 4x minus 2. Upper curve is the same 2 square root of x, so nothing changes here. Now for the range of the x variable, it's going to be between 0.5 and 1. So x has to be in between 0.5 and 1. So there you go. If you work on this, and after some, once again, painful and lots of hard work, they should come out to be equal to 12.4. Okay, make a note. After lots and lots of hard work, lots of work, you should get this same 12.4 as the last approach that we did with type 2. But if I could choose, I would choose the previous one, because even though this one is long and complex, I just need to do the double integrals once. Make a note right here. Double integral once. Well, even though it's painful, it's just once. But here it's painful and you have to do it twice. Okay, double integral twice. So if you can choose one way, choose the way that minimize the number of the integrals. Okay, so make a note right here. So even though you have the choice in this example, try to choose the approach with fewer numbers of integral, and that should save you some time. Okay, so let's move to the next example, example number 8. First of all, there's a typo right here. This is supposed to be example 7, not 5. So it's going to be about the last example that we just did. In this example 8, we are supposed to calculate the area. So it's going to be a little bit different this time. So far, we have been using the double integrals to find the volumes, right? Volumes between the base and the top surface. But this time, it's going to be area that we need to find. And it's going to be the area of the domain region of example 7. So we need this integration domain R from the last example. Okay, I'm going to start by bringing back all the equations and the lines to this example again. So from the last example, we have this y equal to 2 square root of x as the first curve, and also have this straight line, y equal to 4x minus 2, and last line, x-axis, which is basically the same as y equal to 0. So let's draw these lines in the graph so that we can see the shape of the domain region R again. So we have this y-axis right here and x-axis. Okay, let's start with the, why don't I put y and x right here and start with the first curve, y equal to 2 square root of x, and we did that already and it looks something like this. Okay, now move to this next line, y equal to 4x minus 2, and we need the small scale on the x-axis. 0.25, 0.5, 0.75, and 1. Okay, this is a little bit too close. Let me fix that. Okay, somewhere here, 1. So this is 0.5, and this is 1, and we have these intersections, the first one on the x-axis and the next one right on the curve, where x equal to 1. With these 2 points, we can create this straight line passing through them. Okay, so including this x-axis too, we are going to get this region trapped between them again. So this came from example 7, just the same as last time, same region. Okay, but this time we ask for the area of this region instead of the volume, using this as the base. So it's going to be area that we want to know in this example. That is the main goal. So before anything, let me add some information to this graph. Okay, this intersection happens at y equal to 2. Alright, and here at x equal to 1, and that's why we have this coordinate 1 and 2 for this intersection. For this one, it's going to be x equal to 0.5 and y equal to 0 because it's on the x-axis. Okay, so we want to find, here we want to find the area instead of volume. Okay, but by using double integral, okay, it's a little bit different, right? So far it has been volumes, but this time it's area. So this is going to be a new trick for you guys in this example, area by using double integrals. Okay, so since this is new, I'm going to start by giving you the formula to find this area. Okay, first of all, let me bring back a basic formula that you learned maybe in elementary school or middle school. a long time ago. This is about the volume of an object in three-dimensional space. So we are going to bring this back again from the past, maybe 10 years ago. So we have this volume of 3D object. Volume of 3D object. It's going to be equal to volume equal to the area of the base times the height. You remember that, right? We have been using that a lot. Okay. Volume equal to the area of base of this object times the height of this object. Okay. So, okay. Now, taking a look at this is familiar. We have been seeing this a lot. But what if I change the height of this formula to be equal to 1? What if I set this to be equal to 1? What's going to happen? Here's what happens. We are going to get this relationship instead. We are going to get this volume of this 3D object is going to be equal to the area of the base. And this is only true when the height of this object is equal to 1. So make sure that you have this condition, height equal to 1, and then we have this relationship between the volume and the area of the base. Okay, so far we have been using this double integral, right? And this came from the example 7. We have this 16 minus x squared minus y squared. We integrate this with respect to the differential area over this integration domain that we just drew on the graph R. Okay, so let's put a meaning to this double integrals. So this corresponds to the volume. Okay, volume between base, between R, which is the base. Okay, and between R and top surface, which is the 16 minus x squared minus y squared. So you can make a note right here that this is top surface. Top surface of an object is basically the height of the object, right? So in other words, this is the height of the object. It's at the top. It has to be the height, which means that this that you see right here is the height of object. And I am going to do the same thing as what I did with the formula up here. I am going to set the height of the object to be equal to 1 so that I have this relationship volume equal to area. I am going to set this height to be, right, big arrow, to be equal to 1. And if I set this is going to be something different. Okay, let me see what's going to happen right here. Let me change this. So in the end, we are going to get this double integral over this same integration domain, but this time the inside of the integral is going to have 1 instead because the height is set to 1. Okay, and same thing, differential area. Once we have this height equal to 1, this is going to correspond to something different. It's going to correspond to the area of R, which is the base. Okay, and we utilize this relationship up here to have this formula. So we are going to make use of this in order to find the area of R. Okay, let me fix this. Okay, this is supposed to be area of R, or the base of object. Okay, let me fix this line. It's a little bit crooked. Okay, looks a little bit better. Now, we are going to use this and solve for the area of this domain region R from the last example. So let's start with the double integrals that we have. We have this double integral. I'm going to start working right here. Double integral of this 16 minus x squared minus y squared dA. This is what we had in the last example, but here we are going to set the inside of this integral to 1 so that the result comes out to be the area of the base. So once again, this has been changed to 1. Okay, and it should come out to be area. Now the next thing that we need to do is to determine whether this dA is supposed to be dx dy or dy dx. And we did that already. And we found out that the best way to deal with this region is to define the two curves between the left and the right boundaries. So the left boundary is going to be this. Alright, and that's going to be h1 of y. Alright, and the right boundary is going to be this one. Okay, this is going to be h2 of y. Okay, and this means that this is going to be type 2. So we have decided from last example that it's supposed to be type 2, which means that it's supposed to be dx and dy, which means we are going to pick this one, dx dy, and cross this out. Okay, and we are supposed to integrate between the curves first. I'm going to bring all the equations right here. I'm not going to repeat that again. So from the left curve, this one, we have found this this h1y to be equal to y squared over 4. If you don't know what where that came from, let's look at the example 7 again. So this is the left curve, and that is y equal to. Okay, what about I write it again down here? Inside is 1, and we have chosen it to be this order, dx dy. So this is going to be x equal to, first of all, x equal to y squared over 4. Found that in the last example. Integrate from the left to the right, and this is the right one, x equal to y plus 2 over 4. Okay, y plus 2 over 4, and we get this sweeping from left to right, this arrow. And now we proceed to integrate with respect to y, and the range of y is between 0 and 2. Okay, so we have this starting point for y equal to 0 and ends at y equal to 2. So there you go, we have the double integrals to perform the calculation on. So we are going to start with the inside integration, this one. Alright, now this one we integrate with respect to x first. Okay, so this one is not bad. It's going to be, well, this is 1, right, inside, so integration is has become easy. So we get x out of that. And we are supposed to evaluate this at two value of x equal to y squared over 4 and x equal to y plus 2 over 4. And don't forget the other integration sign right here with respect to y, and starting at y equal to 0 and ends at y equal to 2. Okay, now let's continue over here. So first value of x goes in. Okay, this one goes in. We have this same term showing up equal to y plus 2 over 4. Alright, minus the second term. Second term goes in. Well, we get this same y squared over 4 right here. Y squared over 4 for the second term. So there you go. And we are supposed to integrate this with respect to y, and from y equal to 0 to y equal to 2. So first of all, I am going to take the common term 1 over 4 outside of this integral. I can do that because it's a constant. Okay, this is equal. Alright, I'm going to take this 1 over 4 outside. So what I have left inside is this. Y plus 2 minus y squared. And we are supposed to integrate this with respect to y. Once again, y equal to 0 and y equal to 2. So what do I have here? I have this 1 over 4 outside. Integrate inside these terms. I am going to get this y squared over 2 plus 2y minus y cubed over 3. Right? Easy. Just integrate with respect to just one variable. And I need to evaluate this at two values of y. Y equal to 2 and y equal to 0. And let's continue over here. So we have this equal to 1 over 4, still the same. And 2 goes in, it becomes 4 over 2. Okay, and we have plus 4. And 2 goes in, we have this 8 over 3. Okay, alright, minus, we have another term. 0 goes in, like this one, here, here, and here. And you can see that we get 0 out of that. Okay, I can get rid of this one. Okay, what about I put it like this? This is better. So in the end, we have this 1 over 4 times 10 over 3. So in the end, we have this 5 over 6 as the area of this domain region R. And the unit for this is going to be square unit, unit square. So in the end, we know that this area is equal to 5 over 6 square unit.